Okay, so now we're back, and we're going to continue here. Here, I thought we should review. It doesn't hurt to review stuff, so review some of the ideas that we talked about in class. Okay, so I'll define forces, loads, and reactions first. So a force is a push or a pull. A load is a force applied to a structure. Remember, forces are vectors, right? So a load can be the force due to the weight of the structure, the weight of vehicles, snow, wind, whatever. Right? If I'm standing on the bridge, I'm a load. Okay? And the reactions, of course, are the things that resist the movement of that force, that load that we're applying. And these are typically at the abutments on a bridge. And again, remember, forces are vectors, so we're gonna look at that as well. Okay? So remember Newton's first law: an object stays at rest unless it's acted upon by an unbalanced force. So we want our bridge to stay as it is. We don't want it to move, right? So here's an example that I stole and used in that first mechanics video that hopefully you've watched. Okay. If I apply a load to this simple structure on the table, let's say a 10 Newton load, there's two reactions on the table, right? And they're equal because the load is in the middle. Right? Okay. Now, when I have a member, this is a member, let's say a bar. There's no deformation, but if I pull on it, it will extend, right? Certainly if it's elastic like steel, it will. But even paper will pull a little bit, right? And compression, it shortens. So with this simple structure, my handles are in compression and the string at the bottom is in tension. Kind of know that intuitively, right? Because when I push on the top, of course, these bottom things want to slide to the right, so this string is holding it together. So it's pulling back. Okay. Now these big arrows I have here, these are external forces, right? I'm pushing on it from the outside of this structure, and the reactions are external as well. The internal forces are the things I use to figure out how big the handle needs to be in order to keep from breaking. Okay, so now you should have your glue should dry a bit, so you can pull out the pins. Carefully separate, the upper half, the T-shapes, from the plastic wrap. And keep this lower half with the tubes where it is, and then then put a bead of glue on these tubes, and take the T-shape and glue it down. So now this forms a complete truss. That's your bridge. That's one side of the bridge, right? So you'll have two of those. Each team has two of these completed trusses, right? We're going to put them together in a few minutes. We're going to let the glue dry for a while first. Okay, so how did we get those sizes? So for a given load of the internal forces, tension and compression, all members feel those, right? So how big do the members need to be? And what should they look like? That's what we're going to talk about here. So we're going to model the structure as I mentioned, right? So we'll define the supports and do a free body diagram just like I did in class. We'll calculate the reactions, and then we'll use the method of joints to find the internal forces. Just like you'll be doing in homework, like we did in class, and if you watch the other videos up on Blackboard, I've gone through this process quite a few times. So here's a free body diagram. Notice it's a schematic drawing of the figure to some scale, showing dimensions, labeling the points, and drawing in the external forces. So that's 2.5 kilograms per truss because you've got two trusses, right? one on each side. And the reaction forces are here, like this. So this is the free body diagram. Now our first step is to find the reaction forces. Now this one's a little simpler than the examples I've used in the examples in my other videos, because the load is right in the middle. So we know these reaction forces are equal to one another. Right? So now let's first of all convert this mass to a force. So it's 24.5 newtons. Right? 24.5 newtons. And therefore these reaction forces, because I know that I have to push up with the same amount of force that I'm pushing down. Right? And I know they're equal. Right? So everything is symmetrical, right? The load is in the middle, so the reactions are equal. If the load was off center, then they wouldn't be equal. We kind of know that. We've done this already in class. So I know that these are equal and that they're equal to 24.5 total. So they're each equal to 12.3 newtons. I round it up to the nearest tenth of a newton. Okay, so this is that's the first step. Now we can start using the method of joints. Okay. Okay. And we're going to isolate joint A. Now there is a step that's missing here. If you may remember, we didn't check this like I did with the other structures to see if this is statically determinate. Remember the number of unknowns and all that stuff and number of equations. Take my word, this is statically determinate. It might be a little good exercise for you to do that on your own. Okay, so we're going to take joint A out of here, okay, and isolate it. And the internal forces in A are this horizontal force toward B. And notice we don't know what it is, so we assume that it's in tension, right? We don't know. Remember, we always assume tension. And this one is toward point D. Okay. So of course I have a problem here. This is a sloped vector. I need to get the vertical and horizontal components of AD. So these forces, though, we know are in equilibrium because we don't want A to be moving. So I can find the summation of horizontal forces and vertical forces. I can use these equations to find these unknowns here, these two unknowns, two equations, two unknowns. So I need to break AD into X and Y components. Okay. And I'll do that on this next slide here. Wow, big arrow. So this theta is the angle, and I can use that. This is a right triangle. I can use the sine to get the vertical component and the cosine to get the horizontal component, X and Y. Right? Just like we've done before in class. Except these are nice slides, but cosine is the adjacent x and sine is the y, and both divided by h. Right. So now I know that the vertical component of AD, force AD, is equal to the force itself, the hypotenuse, times the sine of this angle, which in this case is 45 degrees. Okay, so this is the calculation that I can do. So now I can find out what FAD is, because I'm going to use those summation of x's and y's to figure this out. First of all, replace this with the horizontal and vertical components, and then, okay, now I've got two unknowns here. That's not going to do me any good. All right? But in this equation, the verticals equation, I only have one unknown. This is the vertical component of AD, right? And I had assumed that it was in tension, but it came out negative, so I know, therefore, that it's in compression. And when I stick it back up here, I come out with AB. AB is positive, right? So that's in tension, and this is in compression. Okay. So now I know those two, and I can isolate the next joint, B. And when I do that, I have, well, I know F sub BD right away. That's an easy one. And because I already know AB, I know BC because those are equal. So that was an easy one. Right? So that's how we got these internal forces. They're all that's it. That's the end of the analysis for using the method of joints. Now what I need to do is use this information to size the members and figure out what the shapes should be. Now remember, in compression we want to use tubes. In tension we want to use bars. Do the results make sense? I don't have any answers that are in the hundreds, right? So it all looks good. Tensions and compressions seem to make sense. Okay. So now what you're going to do is just finish off the truss, trim off the little pieces. Oh, okay, just trim off the pieces. We're going to finish off the truss in a minute, but you remember we talked about materials testing, and I'm going to go through this quickly. This is our Instron, well, not ours, theirs. We have one. It's a nicer, low-budget testing machine. I've already gone through this explanation. And we've already done all of this. It's all online. Okay, these are the experimental results. And I want to get to this. Okay, here we thought. Wait a minute. Jeez. We've already talked about all of this. I wasn't aware we were going to have all this stuff here. Okay. So we're going to do a factor of, we'll figure out the factor of safety that they used. So here's the tension graph that we got from our laboratory. And it plots strength against width. Our doubled 2mm bar is equivalent to a single 4mm, and it can withstand 26 newtons before it breaks. And you may remember the force in there was 12 or something like that. So the factor of safety they used was 2. So it's okay. Right? Typically it's about 1.6, as I mentioned in class the other day. For the tubes, the length of the tubes is 21 centimeters, can withstand 80 newtons. It only needs to withstand 17 newtons, so factor of safety there is quite a bit. You probably could have used a smaller tube. Okay, so now we're going to assemble the final bridge. You've got the two halves, the two trusses. Now what you're going to do is put them together with these cross tubes. Okay. So you have these 6 centimeter tubes. I believe they're 6 centimeters. Cut off. Do a line there, and then cut the corners. Just cut the corners and fold them back. See, like that, and then put glue on the edges, on the ends there, on those flaps, and then use those to glue the flaps onto the trusses, right, like that, and then hold them together. Right, this isn't your bridge; it's a different bridge, but it's the same idea. So you have 2 of those things for yours. See, there's two cross tubes here, one there, and one over here. And then you have a couple of these small 2mm bars that you want to glue on each side for stability. Okay, and we're going to test this structure later on. But so now you should go ahead and glue your trusses together, and that's it.